Hi, I'm Aravindh, and I'm here today to talk to you about an advanced combustion strategy called gasoline compression ignition, or GCI. It is a promising strategy that can be used to improve on diesel for meeting future emissions regulations, but so far it has not taken off because of a major issue of combustion instability at the low loads. Today, the specific topic that I'm going to be talking about is how I used cylinder deactivation to solve this problem. An outline of what I'll be going over today, an introduction to the problem and why you should care about GCI, background on GCI and the stability issues, and then I'm going to get into the methods that we use for the study, both for the experiments and simulations, and then finally the results. Most of the current approaches to meeting future emissions regulations come from improving the two existing engine types, which are spark-ignited and compression-ignited engines. Spark-ignited engines dominate the light-duty sector. They operate on gasoline fuel, so they have low soot emissions, but the nature of the combustion process means that they have high greenhouse gas emissions due to low efficiencies. On the other hand, CI engines operate on diesel fuel. Because they use diesel fuel, they make high soot emissions, but the nature of the combustion process means high efficiency, so low greenhouse gas emissions. One of the more promising approaches that we believe it will take off in the future is the use of gasoline in CI engines to combine the respective advantages of both of these styles of combustion. There are also economic benefits to GCI on top of the emissions benefits that I just talked about. Consider this plot of the fuel demand based on sector that is shown here. The projected demand into 2040 tells us that the heavy-duty sector is projected to grow, whereas the light-duty sector is expected to stagnate. Contrast this with this plot of the same fuel demand now divided according to the type of fuel. We see that diesel fuel is expected to grow in demand where the gasoline fuel is expected to stagnate. The takeaway from these two plots is that if we find a way to use all of that excess gasoline in the heavy-duty sector, that could create some major economic benefits for the end user, making this also economically worth doing. Some background on GCI. Was first proposed and demonstrated in 2006 by Dr. Galgadi, the paper that they published. The reference is down here below. In the 15 years since that time, a lot of research has been done that shows that those emissions benefits that I was talking about a couple slides ago in terms of low greenhouse gas, low soot, do exist. The problem is that those benefits primarily exist at the medium and high loads. But at the low loads, there is the issue of unstable combustion. Take a look at the plot on the right, which shows the operating map of a typical medium-duty engine. You see that large blue region where GCI is stable and where you see those emissions benefits that I was just talking about. The problem is that little red and yellow band down below where GCI is unstable. To access those emissions benefits up top, you need to figure out how to access these or get around the issues down here at this red band below. That is the topic that we're proposing, which we're saying cylinder deactivation at those low loads could help us avoid those regions where GCI is unstable, leading to being able to access the benefits at the higher loads. If we are deactivating cylinders, then there are fewer operational cylinders. So to make a given engine load, those fewer operational cylinders need to be operating at a higher load, which then means that they're in a stable region, and so they're not going to have any instability issues. But first, let's take a second to understand what it means for combustion to be unstable, because that's not something everybody may be familiar with. Technically speaking, combustion instability is the cycle-to-cycle variation of combustion. If I measure 500 cycles of data and I plot the pressure trace for every one of those, how much does it change? Or if I plot the heat release trace, how much does it change? Technically speaking, mathematically speaking rather, it is quantified by using the coefficient of variation, or COV. In this presentation, I'm just going to call it the instability, but you should know that mathematically we're calculating that by using the COV of 500 consecutive cycles and measuring the GIMEP and then calculating the COV of that. But for an idea of what it looks like practically, take a look at this heat release plot that is shown on the left. This is a high load, low instability condition. So a high load, stable condition, and the heat release plot is shown in black. The variation of that heat release plot over those 500 cycles is shown in red. As you can see, there's not a lot of variation, which explains why the instability is so low. However, take a look at this plot, which shows a low load, unstable condition. Again,